then we will get started lecturing. So why not start at chapter 1? It seems like a good chapter. So we're going to start at chapter 1. As I mentioned last time, a reminder that, again, our book here is sort of set up a little bit different than a traditional textbook. Here we do start with atoms first, like the name implies. So we get into the atom, electron configuration, all that kind of stuff right up front. Then we kind of go back to some other things. As we talked about last time, again, the kind of conversion, significant figures, that type of stuff, again, is like more like a pre-chapter in this book. And again, we'll do like a little bit of that on that lab day that we have scheduled. So we'll get started here with chapter 1. Chemistry. Chemistry really is sort of the study of matter, and chemistry does sort of fall into all aspects of our life. Food chemists, chemists for like pharmacy, shampoo, makeup, all kinds of places. And one of the big sort of things that we look at in terms of chemistry is matter. And there are, as you hopefully know, kind of 3 states of matter. There is the solid state, and in the solid state of matter, everything's usually packed in there pretty tight to one another. There's not a lot of room for movement, and that is a little bit in contrast to the second state of matter, which is liquid. And again, in the liquid state of matter, everybody is still, relatively close to one another. One of the sort of major differences, obviously, between, say, solid and liquid is in the liquid state, everybody has a little bit more energy, so they're able to sort of move past each other. That's why, obviously, when we look at liquids, right, they are fluid, they pour and stuff like that. And then, obviously, we get to our last state of matter, which is gas. And in the gas state of matter, everybody at that point is completely broken apart from one another. They actually have a lot of energy, obviously, because they're flying around. As there are collisions as they're flying around, that creates pressure that we associate with gases, which obviously we'll talk about when we get to the gas chapter, and a lot more sort of energy. Also, a reminder, right, these notes are up on Canvas if you do want to use them as well. So one of the things we do talk about a lot of times in chemistry is, matter, how it goes through chemical reactions, how maybe it changes state. And one of the things you also probably familiar with, again, is the sort of changing of state that occurs as we go from, say, solid to liquid. That is the process known as melting. When we go from liquid to solid, that is the process known as freezing. If we go from liquid to gas, that is the process of evaporation or vaporization. As we go from gas back to liquid, that is the process of condensation. We also have sort of a transition of going from, say, solid directly to gas, again, skipping the whole liquid cleanup stage. That is what is known as sublimation. And we could go backwards as well. If we're starting the gas, we could kind of skip the liquid phase and head back to solid. That is known as deposition. Right. Now, sublimation, right, is something like dry ice that you might be familiar with, right? If you've ever used dry ice or seen dry ice, it goes from obviously the solid state directly into the gas state. There's no liquid sort of cleanup in between. And in a later chapter, we will sort of find out why you don't get that kind of liquid sort of state to occur under normal conditions. One of the reasons is actually for it to be liquid, you need a lot of pressure and a difference in temperature at our time here to get it into the liquid phase. Deposition is the process. Maybe you remember CDs, DVDs, they're really shiny. That's how they deposit metals on those things to make them really, really shiny. So one of the other major things that we study in chemistry, which we don't maybe study in this class, but maybe study in the next class, is energy, and energy sort of associated with these sort of processes. As you may know, if I go from solid to liquid to gas, does energy need to be kind of put in to do that, or does energy need to be removed to do that? What do you think? You need to put energy in to do that, right? So if you think about just an easy example, an ice cube, right? If you take an ice cube out, it starts to melt. You have liquid water, might want to make some pasta, right? You put some fire under it, you boil it, it becomes steam, right? So all those are processes where energy is put in to do that. By the way, heat transfers from right? The hot object to the cold object. That's how the heat transfers. That's why when you take out a piece of ice, it just starts to melt, because when you take out the ice, the room temperature is actually hotter than the ice. So the energy from the room actually goes into the ice cube and causes it to start to melt. That's, by the way, also how you freeze water to make ice. When you put room temperature water in the freezer to make ice, that room temperature water is now hotter than the freezer air, and the energy from the water you put in there, thank you, is going to be removed, and then everybody's going to come into the solid stage as they lose that energy. So one of the important sort of aspects of energy is these are all processes where energy is absorbed. And in chemistry, when energy is absorbed, that is known as an endothermic process. And that would mean, obviously, opposite of that, if we go from gas to liquid to solid, those are all really processes where energy has to be removed in this situation. If you just think about gas molecules, they have a lot of energy, so they're flying around with a lot of energy. As you remove that energy from them, they come in contact with each other. They no longer have enough energy really to escape one another, and they kind of stick, if you will. And if you continue to remove energy, they will obviously fall into the liquid phase. And if you continue to remove energy, they will then kind of lock up a little bit more there, because they're not going to move very much, and they'll end up in the solid stage. So those are all processes as we go from gas to liquid to solid that it requires energy to be removed. And in chemistry, when energy is removed, that is a exothermic process. Now, these sort of processes do occur, for example, at a particular temperature. And does melting and freezing occur at the same temperature or different temperatures? Actually, melting and freezing does actually occur at the same temperature. So, for example, for water, that's 0 degrees Celsius, right? For water, that is a normal melting point, freezing point, basically, of water. What happens at exactly, for example, 0 degrees in the case of water is you actually have both phases happening at the same time. So if you think about water, kind of like ice crystals, got a little bit of solid ice, got a little bit of liquid water sort of happening. It's really not until you kind of transition a little bit above 0 degrees that it fully transitions to liquid water. And when you get a little bit below 0 degrees, it fully does transition to ice. The same thing over here when we talk about evaporation and condensation, that occurs really at the same temperature as well. That is the normal boiling point, for example, for a substance. And for something like water, that is 100 degrees Celsius. And it really depends sort of what you are doing when you're at those temperatures, either 0 degrees or 100 degrees, if we're talking about water. Obviously, if you're at 0 degrees and you continue to put heat in there, you will go towards the liquid state and continue that process. If you are at 0 degrees Celsius and you continue to remove energy, you will go the other way, and you'll go towards basically ice and solid basically forming. So a lot of what we study in chemistry has a lot to do with transitions of states, matter, and the different sort of phases they go. And just in general, obviously, we look at chemical reactions that occur and how things react with each other, how things resist reactions with each other. These are sort of important sort of information that we get in terms of chemistry. Any questions on that there? All right. So let's talk a little bit about matter is composed really of tiny particles called atoms. Atoms are really the basic representation of elements. And as we'll talk about actually in this chapter, atoms are composed of really protons, electrons, and neutrons, right? And you can think of an atom as a basic representation of any element that we have. And when we talk about atoms, they do come together to make molecules, for example. And you could think of atoms as sort of an elements, which are basically what they represent, as like the basic sort of alphabet. If you do different combinations, obviously, of letters, you get different words. If you do different combinations of the elements and their atoms, you get different molecules, perhaps, as well as compounds. And that does bring up a good sort of thing to talk about. Obviously, here we can see we have oxygen atoms and we have hydrogen atoms, and they come together to make water. And one of the things that usually is true is the compound or molecule, really the compound, usually has very different properties than, say, the elements that make them up. So if you think about water, it's fairly safe and not too hazardous, right? But water is not really flammable or anything like that. But if you have oxygen gas and hydrogen gas, they have very, very different properties than that compound. Same thing if you think something like salt, like sodium chloride. Sodium chloride together makes basically salt, which has very, very different compounds than sodium metal, which is a really soft metal, and chlorine, which is really chlorine gas, which is a toxic green gas. But through the miracle of chemistry, they come together, and maybe you can put some salt on your fries, right, and not die from eating those things. So that's the beauty of chemistry, I suppose. But there is a confusion sometimes people have when we talk about atoms, molecules, and really sort of compounds, or really elements, molecules, and compounds. So let's just talk a little about it since we have it on the slide. Elements, molecules, and compounds, right? So elements are basically pure substances of atoms of only one element, basically, right? So that is basically anybody on the periodic table by themselves. Obviously, it's an element. By the way, a couple of reminders, just in case you're not sure. Most things on the periodic table that are elements, they come as what are referred to as being monoatomic. And monoatomic means that they basically come as ones. So if you had sodium metal, it's basically just sodium. If you had some iron metal, it is basically just iron by itself. By the way, the other thing that sometimes people have a misunderstanding about is if you have any element that is by itself, not combined with anything else, it does not have charges. Yeah, so none of those things have charges when they are by themselves. Things only get charges when they go hook up with other elements in like an ionic compound, when you have a metal and a non-metal that come together. So sometimes when people learn about naming and charges and those type of things, people assume that if you just have those guys by themselves, they have charges. So they are typically neutral. They really don't get charges till they sort of come together for some reasons that we'll talk about in obviously a later chapter. But there are some elements that actually do come not as monoatomic atoms, but they come basically as diatomic atoms, or diatomic molecules is a better word of that. And those are things like hydrogen, oxygen, nitrogen. A lot of these are gases, fluorine, chlorine, bromine, and iodide, or iodine. These are how these sort of elements naturally come. Sort of group 7 on the periodic table, FCl, Bri, hydrogen, nitrogen, oxygen. So they go NO, F, and down. All those guys, when they are by themselves, they come basically as twos. So if you have something like hydrogen, it comes basically as two hydrogen atoms together. You have oxygen, it comes as two oxygen atoms together. Nitrogen, two nitrogen atoms basically coming together. And again, they don't have charges, but they are two atoms that come together. And that is really the definition of a molecule. So for something to be a molecule, the basic definition is you need two or more atoms that are combined, basically. Now, when we talk about molecules, you should think of it as like a basic definition of really all you need for it to be considered a molecule is simply just two or more atoms together. They could be two or more of the same element. They could be two or more of different elements. It really doesn't matter. In order for something to be considered a molecule, all you need are atoms, basically two or more atoms. Like I said before, it could be the same or different. That's why, obviously, these are referred to as diatomic molecules. They come as twos, which means they have two atoms, and they're considered molecules. Now, sometimes people are confused about the difference between a compound and a molecule. The difference between a compound and a molecule is the definition of a compound is two or more atoms of different elements. So that is the big sort of distinction there is in order for something to be a compound, you need to actually have more than one element involved, and you also need two or more atoms coming together. For a molecule, you don't need the two different elements. All you need is two atoms that are basically coming together. That is why if we look at something like H2, that is an element because it basically only contains hydrogen atoms. It also meets the definition of a molecule because it is two or more atoms that are together. It is not a compound because it is only hydrogen atoms that are involved. If you take something like water, which we have here, which if you draw the little Lewis structure of it, looks something like that, I think. We have basically atoms of hydrogen, and we also have atoms of oxygen involved. So this is two or more atoms, which means it meets the definition of a molecule. It is a hydrogen atom and oxygen atom involved, which means it meets the definition of a compound, but it cannot be an element because, again, it's a combination of two different elements together. And for it to be an element, it has to be basically a pure substance of just that element by itself. Any questions on the differences between those things? So when we do write some formulas, especially for molecules, we do use subscripts. And a reminder that when you do see the subscripts, it does go to the element to the left of it. So for example, if we had H2O there, that is 2. And very common in chemistry, we just don't like to write ones. So if you don't see a number there, it's assumed to be a 1, even though nobody ever writes the 1, and you probably shouldn't write the 1. But if nothing is there, it is considered to be a 1, and it would go to the guy to the left. So again, O2 implies basically that that is how many atoms of that particular element you have. Just like we see with H2O there, we basically have 2 atoms of hydrogen and 1 atom basically of oxygen. And they are chemically united here, basically. In the case of each of these, they are all sharing electrons through covalent bonding that we'll talk about when we get to the bonding chapter, but they are basically sharing electrons is how they're held together. When we talk about, for example, ionic compounds, they are held together by a very common sort of idea in chemistry, which is electrostatic attraction, which is a fancy way of saying positive and negative attraction, opposites attract. Yeah, so the positive charge and negative charge are what kind of sticks those guys together. They're actually not sharing electrons in an ionic compound, but it's just simply that attraction between the opposite charges that holds it together. Here, in this case, they are actually sharing electrons and that type of stuff. And obviously, we'll talk about that when we get to bonding. Now, obviously, one of the important things that we look at, as I mentioned earlier, in terms of chemistry, are chemical reactions. And chemical reactions, when we look at an actual reaction, usually displayed by an equation, and on the left-hand side of the arrow are what are known as reactants, and those are our starting material in a chemical reaction. And we get products on the other side of the arrow, which is basically what is formed as a result of a chemical reaction. Now, one of the important things about a chemical reaction that we will talk about in this class, obviously, and in some chapters as we go through it, is we do only break bonds. So when a chemical reaction occurs, the only thing that happens is everybody that's on the reactant side basically just break all their bonds. And they reform into new substances on the product side, and we make new bonds and new compounds. And that's one of the things that a chemical reaction is. It is a chemical change. What you start with and what you end with are fundamentally different things. You can't get back what you formed by any type of physical means like freezing, boiling, or filtration or something like that. You can't separate them back out by any type of physical means. For example, when we make water from hydrogen and oxygen gas, you could do all kinds of physical sort of things to water, like heat it up, put it in the freezer. You will never get the hydrogen gas or oxygen gas back. Otherwise, again, if you go back to making the pasta example, you would never get to the pasta part because you would be making hydrogen gas and oxygen gas, and you probably wouldn't get to that part where you add the pasta into the water that's now exploding. But you can get back, for example, the hydrogen gas and the oxygen gas, but it does require another chemical change. And you can run an electrical current through it and do what is known as the electrolysis of water, which you could do with a 9-volt battery and a little acidic water and some like probes, and you could do that. And you can break it back apart, but that again is a chemical reaction that's occurring and a chemical change that's occurring when we do that. That is also why, as we will talk about, that when we do a chemical reaction, we have the conservation of mass, we have the conservation of elements, because the only thing that we're changing basically is bonds. We don't lose any elements along the way. We don't make any new elements along the way. The only way that can happen is in a nuclear reaction, where all you do is make new elements. But in chemical reactions that we talked about in this class, we basically don't make any new elements. Yeah. Yeah, they can, in a sense, kind of come back together, and it may require some energy to do so. In that sort of situation, you would there in order when you typically do that, for example, you would probably want to collect them, right? So usually, for example, if you do it on a very small scale, which actually I do it at one of the schools we teach at, they actually do the electrolysis of water with a 9-volt battery. They put like test tubes in there and they collect the gas. And the idea of that, probably, if you're going to do that, you would probably, the idea is to collect the gas and probably keep them separate and stuff like that. But ideally, if you let them kind of come back together, they can reform water. And it may not be maybe in the liquid phase at that point, but it may be maybe more like water vapor and stuff like that. It may have to go through some changes. Other questions? So again, in a nuclear reaction, which we don't talk about in here, but if you take 200B, there's a whole nuclear chemistry type chapter where you talk about that. Those reactions actually do involve actually changing, the elements you start with to new elements and stuff like that. And that's because in those type of reactions, it actually involves pretty much always everything kind of in the nucleus, versus in a chemical reaction, it's all about what's outside the nucleus, the electrons and the bonds that occur. So let's talk a little bit about the scientific method. The scientific method is basically, how we approach things. And usually the scientific method is sort of kicked off by an observation. Maybe you observe something happening and maybe it piques your interest. And maybe you want to sort of figure out maybe why that is happening. So usually what you would try to do there is form a hypothesis, which is a tentative sort of explanation of maybe what you're observing. A lot of times you would want perhaps your hypothesis to be something that you could test, a testable sort of hypothesis that can lead to some experiments. And once it leads to experiments, usually that will lead to kind of more observations, maybe observations about what you were looking for, maybe new observations. Maybe you got to adjust your hypothesis, which leads to more experiments. It can be sort of a vicious sort of circle there, especially if you're working for somebody and you go, hey, I didn't really find what we were looking for, but I did find this. And they go, well, that's quite interesting. Why don't you go do some more work and some more experiments and see what's going on? But hopefully at some point, what sort of comes out of it is sort of really one of two things. You could sort of hopefully end up with maybe a theory, or you may end up with a law. And there is sort of a difference between sort of a theory and a law. A theory you could kind of think of as something that, when it is sort of stated, it is thought to explain why something occurs. Now, in terms of a theory, it can be something that at the time, maybe is thought of that's exactly what's going on. But it is something that can be sort of revisited. It can be revisited in the sense of maybe some people down the road do some more experiments and go, well, you're kind of right about this part of it, but this part maybe not so right. And it can be thought of as maybe not being correct in all aspects. For example, we'll talk about in this chapter here, I think, Dalton's atomic theory, which was explaining basically the idea of what atoms are and sort of what's going on. And there are several parts of Dalton's atomic theory that are considered still correct. And there are parts of it that is considered not to be correct because, frankly, at the time, they weren't really knowing about certain things that could occur. And their idea was maybe it's correct. We're also in a later chapter, maybe next chapter, we might talk about Bohr's theory of the hydrogen atom, and that is trying to explain sort of how electrons are transferring. Bohr's model of the atom is more that planetary model where you have orbits and electrons going in pretty circles, which again is not necessarily how it actually happens as we kind of know today. But back then, that is sort of what they thought. And it works really well, for example, in the case of Bohr, to describing what you see in hydrogen, which has one electron. When you move away from hydrogen that has maybe more electrons, it doesn't really hold up. So, a theory can be thought to be correct, but it is not really sort of set in stone. It can be, again, maybe some parts disproven, maybe revise as time goes on and people do more sort of experiments. A law, on the other hand, is something that pretty much every time it happens the same way, no matter what the situation is. Sort of, if you want to think about it, kind of set in stone, if you will. It hasn't been like disproven that, other things could happen in certain situations. So we have laws, right, of conservation of mass, for example, right? And that's one of the things in a chemical reaction that we know sort of occur. Again, if, for example, if you started with like 4 carbons on the reactant side, you will end up with 4 carbons on the product side. And because carbon has a mass of about 12 grams, you'll have about whatever, 48 grams of carbon on the reactant side. And because you still have the 4 carbons on the product side, you should still have about 48 grams of carbon there. So you have that conservation of mass, you don't lose it. Another sort of law of conservation is the conservation of energy. We don't lose nor create or destroy energy, but energy is thought of as sort of always can be transferred. So the idea when we think about energy and what happens with energy is if somebody loses a certain amount of energy, somebody else has to be around basically to gain that amount of energy. So if you think just about, for example, my ice cube example, when we put the room temperature water into the freezer, that room temperature water is going to lose all that energy. It has to go somewhere. Where it goes is obviously the freezer air, right? Picks up all that energy. So we have processes a lot of times where in one case it's maybe an exothermic process for one thing where it's going to release this energy, but there will be somebody else that'll be around where it'll be endothermic and it will pick it up. For example, if you took a room temperature water and you heated up a piece of metal, maybe done this like specific heat in 100 or something like that, put the metal into the room temperature water, because the metal is hotter, right? That metal is going to release all that energy to the room temperature water. The energy lost by the metal should be the amount of energy that's picked up by the water, as that's kind of the only thing that's happening there. How do we know there's sort of the energy change, right? We usually see that in terms of looking at temperature, right? We could see the temperature change to indicate kind of the flow of energy. If somebody's temperature starts low and then ends up higher, it most likely picked up energy, right? And that's why we see a change in its temperature and the rising thing. If we take something that's losing energy, its temperature will actually drop, right? So if you just think about that hot metal, once it goes for a swim, its temperature is actually going to drop down to the same temperature of the water, wherever the water ends up, they will end up there. But that will definitely be lower than the hot metal. So laws are more sort of concrete, if you will, sort of set in stone, if you will. And again, really summarizes what happens, and there's kind of like no indication of that. Same thing, and again with the energy, like the potential energy of the big boulder on the hill, right? Has a certain amount of energy. When it goes, it then transfers some of that energy to kinetic energy as it's moving. When it splats on the ground, hopefully nobody's underneath it, right? But it would transfer that energy to the ground and whoever's underneath it, in a pleasant thought there. And that energy obviously would be dispersed. All right. All right, so we're going to now talk a little bit about really the atoms. And as I mentioned, we do get right into the atoms here. So we're going to talk about sort of, and we're going to go through some experiments perhaps and some ideas of, the model of the atom and sort of what the atom looks like and what helped us sort of understand sort of what the atom is all about. Obviously, it all started a long time ago where they tried to explain what was happening in chemical changes. Uh, and Robert Boyle did a lot of quantitative type experiments. Quantitative experiments are measurements, and that's different than qualitative, where you just make observations. And sort of three important laws we do see in a lot of sort of these early experiments. As I mentioned before, that a given compound always contains exactly the same proportion of the elements by mass. So, for example, if you have water, it always is 2 hydrogens for every 1 oxygen. 2 hydrogens, about 2 grams, right? 1 oxygen, or a 10, it looks like, is about 16 grams. That means for every basically gram of hydrogen, you have about 8 grams of oxygen, basically, in the situation. And no matter where you get the water from, be it in this bottle, more expensive bottle, tap water, it's all H2O. May just cost more depending on where you get it, I suppose. But again, it should be made up of the same proportion by mass of those elements. Law of multiple proportions, which is one that was done by Dalton, when two elements form a series of compounds, the ratio of those masses of the second element combined with 1 gram of the first is always reduced to sort of smallest whole numbers, So if you do something like CO and CO2, right? That is, again, 12 grams of carbon and 16 grams of oxygen in that case. And if you do the ratio basically of oxygen to carbon in this case, divide the two, you get something like 1.33. Now, if we increase, for example, the oxygen here by 2, that's basically 12 grams of carbon, and 2 times 16 is about 32 grams of oxygen present. 32 grams of oxygen divided by 12 grams of carbon gives you 2.66. And if I take 2.66 and divide it by 1.33, that is a multiple of 2, a whole number multiple between the difference between those two is 2, right? And again, we basically increased oxygen by 2, and we increased our ratio by a factor of 2 as well. So this idea of the law of multiple proportions, again, elements will come together. They will come together in these sort of whole number sort of ratios. And also, as you probably know, again, when we do form compounds, our molecules, we never really get like a half atom or anything like that, right? So we get these whole atoms. Those subscripts that we saw earlier should always be whole numbers. They should never be, decimals or half atoms. So these 3 laws were really looked at early on and sort of led into some of our discovery about the atom. And one of the first and important sort of ideas that happened or came about the atom was done by Dalton. Dalton showed unusual talent for math and science. He recorded the weather most of his life every day he woke up. He never married, but probably the most important thing is, of course, he went bowling on Thursdays because that's definitely going to show up on every exam. So make sure you say Thursday, not like Fridays, half price Saturdays, midday. I don't know. But in addition to going bowling on Thursday, which is an extremely important thing to know, he did formulate a precise sort of definition again of what atoms are. And that's known as Dalton's atomic theory. So let's go through some of the ideas and some of the points here of Dalton's atomic theory, which you should know. And again, mine's broken up. The first thing he said is each element is made up of tiny atoms, which obviously is correct. And as we know a little bit later on, obviously they are made up of even smaller particles like protons, electrons, and neutrons. He also said that atoms of a given element are identical, and atoms of different elements are different in some fundamental way. Now, as we talked about earlier, Dalton's atomic theory is a theory, and there are some points to Dalton's atomic theory that are not really considered sort of correct still. One of them is this actually right here, that atoms of a same element are all identical. And they did not know about the sort of the existence of what are known as isotopes. And isotopes are the same element, but they have different masses. And that would then obviously go against what he just said there, which is they're all identical. So they can't be identical if they have different masses. They cannot have different masses if they don't probably have different numbers of subatomic particles that are present. So that's one of the points of Dalton's atomic theory that is sort of found to be incorrect. Another idea that was sort of found to be incorrect, we'll just do the unhappy face there. So another one that is sort of incorrect is the idea that atoms are sort of indestructible. And nuclear reactions, obviously, that's all you're doing is basically changing one atom into the next. So, that also is something that they probably obviously was not aware of at the time. And again, this is the idea of a theory that, at the time it seems to explain everything or maybe partially explains everything. But as time goes on and people do more sort of experiments, perhaps, they're able to point out things that are maybe not so correct. Obviously, the other part of that is correct, that atoms of different elements are different. So if you have an atom of carbon, it is going to be different than an atom of iron or an atom of copper, based on how many protons they have, perhaps neutrons and stuff like that. Another aspect of it is he said that chemical compounds are formed when atoms of different elements combine. And that is, as we talked about earlier, what a compound is two or more atoms of different elements that have come together. A compound always has the same relative number and type of atoms. So as we were just talking about sort of the proportion there, they will come together in these sort of whole number ratios. And again, if we're talking about, for example, water, it's always going to come together with two hydrogens and an oxygen for it to be water. You won't have water with, nitrogen and other things in there as well. He also said that chemical reactions really only involve the reorganization of atoms, changes in the way that they are bound together, and that is correct as well. So as we were talking about earlier, in a chemical reaction, that is essentially all that's taking place. Is basically we're just breaking bonds and making new bonds. That's essentially all that's happening, and that obviously is correct. Atoms themselves, again, are not changed in a chemical reaction. That also is correct. Again, we have that conservation of mass as we saw in that video and we've talked about. Again, if you have the 4 carbons we talked about earlier and you started with it, you should, again, still have those 4 carbons when the reaction is over. Once again, they may just be in sort of different compounds along the way. All right, so let's take a look here and see which of the following statements regarding Dalton's atomic theory is still believed to be true. Let's start with the first one. Elements are made of tiny particles called atoms. Is that true? gonna say yes. I think I heard a yes somewhere there. I got a thumbs up. I like that. That works as well. All atoms of a given element are identical. That is not so good, right? A given compound always contains the same relative number and types of atoms. That is good. And atoms are indestructible. Not so good. So it looks like, I guess to answer the question, 1 and 3 are still good. Uh, and obviously 2 and 4, not so good. Yeah. Any questions on that? So you do need to know Dalton, again, bowling on Thursday. You also need to know the different parts of his atomic theory. You need to know which things are not so correct, right? And obviously which things are correct. All right. So Dalton's sort of theory was really good. It obviously led to sort of other theories, and we'll actually talk about these guys when we get to the gas sort of chapter. But Guy Lusick did a lot of work with gases, and he worked under pressure and temperature sort of differences, and so did Avogadro. And one of the things that he saw was as the temperature, for example, in the Guy Lusick's, as a temperature went up, so did the pressure again, because as we'll talk about, gas molecules are moving around a lot faster, a lot more collisions, and that's also because the volume is fixed, so they have nowhere to go but bang into the walls as they're moving around a lot faster, causing a lot more collisions, and vice versa. As the temperature goes down, you will see a decrease in the pressure as well, because they're going to be flying around a lot slower, going to take longer for collisions to occur, not going to have as much pressure. Avogadro, our guy there that likes his number, also had a gas law as well. And basically, what he saw was under constant pressure and temperature conditions, the volume of a gas will actually equal the moles of the gas that you have. So, one of the sort of concepts and ideas that you could do with, say, Avogadro's law in gases is you could kind of do like a stoichiometry calculation, and instead of using mole to mole relationship, you can actually use like a volume to volume relationship, because they're essentially equal in that sort of conditions of constant pressure and temperature. And we will revisit that for sure when we get to the gas chapter there. And we'll look at that later on too, I think. All right. So as I mentioned, Dalton pictured compounds as really collections. And again, here we have NO2, we have NO, NO and N2O. And again, each of these are obviously a combination of two of the same elements, nitrogen and oxygen. And as I mentioned earlier, you can think of the elements as like the alphabet. And again, based on the combination you put together, will give you a lot of different words that we used to put in dictionaries. But here, again, the different combinations, different amounts of those elements, and also different bonds that are associated in that process when they come together, will give these guys some different properties, even though, again, they're ultimately made up of really the same two elements in all these cases. So, based on Dalton's atomic theory, a couple of important ideas were really thought of. Again, it was thought that the atom was the basic unit of elements that could come into chemical combination. There was a lot of experiments that was done afterwards, which basically showed that although atoms are extremely, extremely small sort of particles, they also contain even smaller particles. And those are, again, sometimes referred to as subatomic particles. And those subatomic particles are protons. And as we'll talk about, as you probably perhaps know, those are positively charged particles. They are electrons, which are negatively charged particles, and they are neutrons, which basically have no charge in that situation. And what we're going to talk about now are some experiments that led to sort of our understanding of each of these sort of particles and maybe where they are in the atom. And so again, as we go through it, we'll talk about sort of what you need to know from those sort of experiments. So let's get into it here, perhaps. One of the first things that really led to the understanding of the electron and was done by J.J. Thomson. And J.J. Thomson did a lot of work with cathode ray tube, or CRT, sometimes referred to. And you may be familiar with CRT. Maybe you've seen an older TV that used to be, a lot of times they used to be on the ground, and they have a big back there, a picture tube in it. Those are CRT. Old computer monitors that have like the big back that comes out like that, those are CRT monitors. And one of the things that was very, very important in these sort of experiments is that idea of sort of opposites attract, right? So again, as we talked about before, positive things are going to be attracted to negative things, but two positive things don't really like to be near each other. Two negative things don't like to be near each other. They're really repelled. And a lot of these experiments, for example, use that to sort of their advantage. Just for example, if you have an electrical field where you have obviously a positive side there and a negative side, again, just by that idea of opposites attract, if you shot a beam and it kind of bent up towards the positive side, that would probably mean that that beam has what type of charge? Yeah, it'd probably have a negative charge. Same idea if you shot a beam here and it kind of bent towards the negative side, we could probably deduce that perhaps that beam was positively charged. And obviously, if you shot a beam and I could draw a straight line, just imagine that's straight. And it really didn't bend either way towards the positive or the negative. It probably would have no charge, that sort of thing. So the use of electrical fields and also things like magnetic fields, which has a north pole, south pole, kind of works similar, uh, was thought of and used a lot in this. And a CRT tube basically is a tube that has a negative side and a positive side to it, and basically shoots negatively sort of charged like electrons. And because of that, what's going to happen is those electrons are going to travel away from the negative side and obviously towards the positive side. And a lot of times they will put something on the end here where it will be able to sort of fluoresce and you can kind of see where it's hitting it along the way. And Thomson used a CRT tube such as this here to figure out the charge to mass of an electron, and that was basically what was found. This is a CRT tube. I don't know if it'll play. Maybe it will. There we go. Maybe. There we go.
It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So again, that demonstrates, I was just talking about something like a magnetic field. We know that beam obviously has a charge that's affected by a magnet. It would also be affected by a electrical sort of field as well. Yeah. Exactly, and like years ago, your parents probably didn't tell you that, but they used to tell you when you sat in front of the TV, you shouldn't do that because things are shooting at you. Yeah, like because the picture tube basically is a cathode ray tube. They used to call out TV repairmans, right? And they would actually come out to your house and pull out your back of your TV and your picture tube and stuff like that. We wouldn't just go to like Costco and grab a new TV, right, and throw it on there at Super Bowl time. But yeah, that's why a lot of those things are affected, can be affected like that. You put that in really old TVs, you do something like that, and all of a sudden the picture's like wavy and stuff like that because that's basically affecting it too. Yeah. The good old days when you actually had the TV repairman come to your house, right? All right. So Thompson, as I mentioned before, did a lot of work with it. There he is. And again, what he was able to really determine in terms of an electron was he was able to determine the charge to mass of an electron. So this was really good sort of advanced idea of what is going on with an electron. The ratio there of the charge to mass was minus 1.76 times 10 to the 8. C is a coulomb. That's a unit of electrical charge divided by grams, which is obviously a mass. You don't necessarily have to know that number or anything like that. But you do need to know that Thomson obviously used CRT tubes or cathode ray tubes and was able to figure out the charge to mass of an electron. And the next sort of important experiment that kind of goes with what Thomson found was one that was done by Millikin. And Millikin did what is known as the oil drop experiment. And much like the title implies, it involved oil. And basically what Millikin did, and we have a little video there, an animation in a second, but he basically had a chamber, and in that chamber was basically an electrical field, and basically shot in oil droplets and atomized them, and there's like a little hole here. And just by gravity, that oil droplet was going to, as it starts to fall, sort of pick up a charge. And what Millikan was able to do was he was able to adjust the electrical field in such a way that basically, I'll just make my oil droplet bigger. The oil droplet was able to basically just be suspended. So he was basically able to kind of really adjust the electrical field in such a way that, the droplet wouldn't fall or anything like that. And what he was able to sort of get out of that was actually the charge on an electron. So Millikan, through his oil drop experiment, was able to figure out the charge of an electron. Maybe. So again, there you can see. And again, he was able to really adjust electrical field. And again, it would just kind of be suspended there. And he was able to figure out the charge of an electron was minus 1.6 times 10 to the negative 19 coulombs. And that was really an important sort of combination with Thomson. So if we think about Thomson, Thomson had the charge to mass of an electron. Millikan got the charge of an electron. And if we use both of that information together, like take the charge of an electron and maybe divide it by the charge to mass of an electron, the charge of an electron will cancel out, and the mass of the electron could actually be determined from these two experiments. So Millikan, again, did the oil drop experiment, a little bit about sort of what happened. And again, that basically what came out of it was a charge on the electron. Again, using both of those sort of experiments together, as I just mentioned, the mass of our negatively charged electrons can be determined, and it's determined as 9.09 times 10 to the minus 28 grams. That is a really, really small number, right? So it's like 28 places to the left there, add 27 zeros, right? So it's a very small sort of number. Any question on that there? So these kind of early experiments using the CRT and sort of our oil drop experiment led to our understanding of the mass of an electron and some of its properties, obviously that it has a charge and negatively charged. And this was really helping us sort of move forward and trying to understand sort of the atom. And that led us into really the proton and the nucleus sort of being investigated next, or discovered, if you will. And what they found was a couple of things. By the early 1900s, it was believed, obviously, from these experiments that atoms did contain electrons. It was also believed that atoms were neutral. So if we already know that the atom contains electrons, which are negatively charged, that does mean that the atom would have to contain something positively charged to balance it out so that the atom itself is neutral overall. So around the turn of the last century, the accepted model for the atom was one done by Thomson, and it was sometimes referred to as the Plum Pudding model. And the idea of the atom, or this model of the atom, was that the atom was a sphere of positive charge. So this big sphere, and it had all this positive charge. I'll just draw as red, spread out over here. So all this red is like positive charge. And it was believed that within this sort of big sphere of positive charge, they had these electrons embedded inside, like plum pudding, which is like a pudding with raisins kind of dropped in it. And the raisins are like the electrons, pudding's like the positive charge that's basically spread out. And one of the other major things that they believed at this point in terms of this model was that most of the mass of the atom, as it says there, was actually the electrons. So they believed that at this point, the electrons actually made up most of the mass of the atom. And this was sort of the accepted model of the atom at this point, based on sort of early experiments and everything that was sort of done at this point. And again, this sort of model or theory of the atom, as we'll soon talk about, again, may not hold up as we kind of continue down the road here. And here's maybe a prettier picture of that. Again, this sphere of positive charge is really just spread out all over it. Again, these electrons sort of embedded inside. So the next major sort of step forward in terms of understanding the atom really came with the gold foil experiment. And the gold foil experiment was one that was done by Rutherford, Geiger, if you ever did radioactivity, Geiger counter, and Marston. And they used alpha particles to probe the structure of an atom. And as I mentioned before, there are particles that obviously can be affected by electrical fields and also magnetic fields. And a lot of these experiments that were done used a lot of radioactive type particles. And there's three sort of main radioactive particles that really do come up a lot. Alpha particles, and these are basically positively charged radioactive particles. They're essentially the helium nucleus. And there's also beta particles. Beta particles are negatively charged particles, and they're essentially an electron. And there also are gamma rays, and gamma rays are pure energy, has no charge. Yeah. So you can see these three are sometimes, oftentimes used because, you know, they are relatable to basically what's in the atom. Protons, which are positive, electrons, which are negative, and obviously gamma, which has no charge like neutrons. So Rutherford used alpha particles, and what he did is he shot these alpha particles at pieces of gold foil with the understanding that I think the atom is what just came out, which was the plum pudding model, and I think that is what the atom is. Now, what he expected to happen and what actually happened were kind of two different things. So if we think about our plum pudding model there that I drew on the previous page, we'll go here. So if I shoot these alpha particles, for example, which are these positive, heavy moving particles and fast moving particles, and I shoot it at basically this kind of big old diffuse pudding a positive charge, it probably would go through. So for example, if I grab something I might not need there, how to do that one. So for example, if I took this as my atom, right? And we'll just pretend it's circle, but we'll go with it. And this is all my positive charge, right? And if I held this side and somebody else held that side, and for example, we were able to shoot my pin at it really, really fast, right? It most likely would go through, right? With some deflection, right? Because it's going to hit something and kind of maybe deflect a little bit as it's going through. It's moving really fast, right? This is really, really tight. And that's sort of what they expected to happen. So when they shot these alpha particles, because they're positively charged and they're moving really fast, they're going to hit this pudding a positive charge. So they kind of expected, you know, these guys to go through, but there should be some deflection as they sort of pop through all that positive charge, because it is still like and like sort of coming at each other, but it is going to be able to kind of pop through and go through. And they were really surprised when they sort of did this experiment that that is actually not what they saw. And what they saw was when they did shoot these alpha particles at these pieces of gold foil, pretty much most went through undeflected. Thank you. Most went through pretty much undeflected. And that was really, really sort of shocking to them that most of them just kind of sailed through no problem. But they did also notice that every so often they would see an alpha particle like bounce off at these really large angles, maybe even come back to its source. And that told them a couple of things. First off, if it just went straight through with no problem, what did the alpha particle hit? Pretty much hit Nothing, right? So if I take my pen example, I throw it that way with nothing in its way, it's just going to sail through, right? No problem. It's not going to get deflected or anything like that, right? But every so often, they did notice that these alpha particles were bouncing off at these really large angles. That meant that these positively charged alpha particles, in order to bounce off at really large angles and even come back to where they were shot at, had to hit something that was what type of charge? Something that was really, really positive, right? Because positive and positive don't like each other. So they had to hit something really, really positive to make those alpha particles bounce off. So this sort of threw a wrench into the idea of the plum pudding model of like the positive charges spread all out, because if it was, it should be able to bounce through and let some deflection, but really get through there. So they sort of had to abandon it and kind of come up with the idea, well, maybe this is my atom, and maybe the positive charge is not spread out all over. But if I took my positive charge here and I folded it, and I folded it again, what do they say, like 7 times? You can't fold after 7 times. And instead of my positive charge being way all over the place, maybe I fold my positive charge into something like this, very, very concentrated. Now, if I take my alpha particle and shoot it at it, it obviously is not going to go through. It's going to come right back and hit me. I saved my real pen. I threw the pen I didn't care about at it. So it really did throw a wrench at that. And really what they had to say was, eh, maybe not so correct. Again, another idea of something that's a theory or a model that down the road was found maybe to not be so correct. So now we'll go to that animation here and see what it shows.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles.
So you can see most of them are just in the back, and every so often lit up everywhere else.
This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So again, as we saw in that animation, pretty much most of them just sailed through, but again, every so often, it kind of lit up. And that's going to account for, again, our positive charge really can't be spread out everywhere because we're not getting deflections happening everywhere. It has to be really, really concentrated in sort of one area, if you will. So his findings were, as we've been talking about, again, most went through undeflected. Every so often we see the alpha particle getting sprayed out at large angles, coming back, kind of like, again, shooting a gun at a piece of paper and having the bullet come back at you. Again, not really what you're expecting to happen. So on the left there is, as I kind of drew earlier, sort of what they expected to happen. Again, they expected, based on the positive charge being spread out, that they should be able to kind of get through there with some deflection. But again, on the right is pretty much what they saw. Most kind of went through no problem. And again, bounced off at large angles that hit something that's very, very positive. So as I mentioned before, basically, we had to kind of, based on the results of this experiment, throw out the plum pudding model and go with really our sort of modern version of the atom, which is that the atom is mostly empty space. And again, that's what accounts for the alpha particles basically not having a problem going straight through, basically didn't hit anything, hit that empty space. The atoms have a very dense positive core, which is known as the nucleus. And as we'll talk about later, found within that nucleus are protons, which are positively charged, and around 1930s, neutrons that have no charge were found there. Obviously not at this time, but in 1930s, it was found basically to be there. It was also found that obviously the electrons would be traveling in that empty space. So the electrons are traveling in that empty space at a large distance from the nucleus. And one of the other major differences between the two models of the atom is, in the current model and sort of the correct model, if you will, most of the mass of the atom is actually made up of the nucleus. So not the electrons, but actually the nucleus here. So the idea here is we have our nucleus with our protons, our neutrons, and out in that sort of empty space, we have the electrons traveling. And as we'll talk about, as you hopefully know, electrons actually don't travel in pretty circles and orbits or anything like that. They travel pretty randomly about the nucleus. And as we'll talk about, you really don't know at any given point in time exactly what an electron is or how it's moving. And really, the more you know about one, the less you know about the other. But is there some type of attraction between the electron and the nucleus? The answer is yeah, there is, right? Because electrons are ultimately negatively charged, right? And the nucleus is ultimately positively charged. And that's what holds them, right? So they all just don't go fly away, right? If there was no attraction, the electrons would just take off, right? So they are sort of tied to, as we'll talk about in the next chapter, really the nucleus and that positive charge, like a string, that kind of keeps them there. But they are not, in the nucleus and stuff like that. That is also why, as we'll talk about in later chapters, right, only certain electrons, for example, are involved in bonding, and other electrons are not. The ones that are closest to the nucleus are going to feel the full brunt of the positive charge, and they're going to be held a lot tighter than the electrons that are sort of further away. They're still going to be attracted to the nucleus, which is why they just by themselves don't fly off. But they're not going to be held as tightly as obviously the ones closer, and that's why those valence electrons, for example, are the ones that are involved in bonding, while core electrons, which are closer to the nucleus, are held a lot tighter. So you do need to know, again, Rutherford's experiment, what he did. Remember, he shot alpha particles at things, not an expo pen. And although those are my favorite answers when people write that on exams, yeah, he shot like an expo pen at the pieces of foil and it bounced somewhere. You need to know what he expected to happen based on the Plum Pudding model. You need to know what actually did happen. And obviously, you need to know how we moved away from the early model of the Plum Pudding model to sort of the current model of the atom and what the current model of the atom is. Any questions on that there? So this table is just a table that sort of summarizes a lot of the experiments we talked about. I think it's a little bit bigger maybe in your notes, but you'll be able to see it. But it basically covers the different things that we talked about and what came out of those experiments. Now, protons, as I mentioned before, are these positively charged particles that were found to be in the nucleus, and they have a mass of 1.67 252 times 10 to the minus 24 grams. If you remember, our electron was like 9.09 times 10 to the minus 28 grams. And what that means is the proton is actually about 1,840 times heavier than an electron. And if you think about sort of Rutherford's model of the atom, where he says that most of the mass of the atom is actually the nucleus, this does make sense because in the nucleus we have protons, which are about 1,800 times heavier than any electron that's flying around that empty space, and that would account for most of the mass of the atom in that case. So at this point, scientists perceived the atom as follows. Again, the atom is relatively small. It has this internal structure of the nucleus where protons are housed. You could think of the atom as the size of the Superdome or a really big, like, football stadium, if you will. And the nucleus is basically like on the 50-yard line there, like a marble there on the 50-yard line. So a lot of big empty space where we have electrons flying around. Very small part of the atom, but actually most massive part of the atom is that nucleus where we have it. If you ever been to the Superdome, the seats are like this. You feel like you're falling out of the seat if you sit in it. Even when you're sitting, you're like, I feel like I'm gonna fall. It's very, very high up there. So the neutron was also discovered. So for a long time, it really was believed that in addition to protons that are in the nucleus, there was another subatomic particle. And it really wasn't until 1932 that a guy by the name of Chadwick sort of discovered. And what he discovered, he did a lot of experiments and he saw that there was a lot of this really high energy radiation that sort of came off of his experiments that really resembled gamma rays. And remember, gamma rays have no charge. And basically, that was the idea of understanding that the neutron really has no charge. And they were able to discover the mass of a neutron as being 1.67495 times 10 to the minus 24 grams there. And that actually, if you go out like 3 or so decimal places, that actually beats out the proton as being the heaviest. And actually, the neutron is the heaviest of the 3 particles, with the proton being very close to it, but just slightly less heavy. And obviously, the electron being a lot less heavy and massive. That again sort of reinforces the idea that most of the mass of the atom is made up of the nucleus, because again, in the nucleus, you have protons, which is about 1,840 times heavier than an electron, and you have neutrons, which are also 1,840 times heavier than an electron. So again, that sort of reinforces the idea that no, it is not the electron that's most massive in there, but it's actually the nucleus, which contains these particles, which are way heavier than any electron that's basically flying around. You obviously call these particles neutrons. So again, you can see the comparison of our 3 particles with our neutron just edging out our proton, and again, our electron being much, much smaller. A reminder as well, when you look at a negative exponent, the smaller negative number is the larger number, because in the case of minus 28, you're going 28 places to the left, putting 27 zeros, making it a lot smaller than only going 24 places to the left and putting 23 zeros, right? So again, sometimes people, when they look at the exponent, think, isn't 28 bigger than 24? But the negative is really important there when you're analyzing that. Any questions on that there? All right. So again, the atom contains, as we saw, electrons outside the nucleus in that empty space flying around, protons and neutrons in the nucleus, protons being positively charged and neutrons having no charge. And again, our massive nucleus more heavy than our electrons. I think that's actually a good stopping